Welcome back everyone. In this video, we'll be looking at an interesting phenomenon still attracting researchers around the globe. If you've already heard of thermoacoustic devices, then you've probably knew that heat can be converted to sound, and sound could also be converted to heat. The former is the point behind thermoacoustic engines, while the latter describes thermoacoustic refrigeration. It's widely spread that long time ago, glass blowers in Europe used to hear sounds out of the glass tubes when attached to a hot bulb. In year 1777, a guy named Byron Higgins became the first to mention this effect after attempting to experiment it. Higgins moved an open tube vertically over a hydrogen flame backed by a fuel supply and noticed sweet tones coming out of the tube. This experiment is referred to as singing flames. However, in 1859, a very similar experiment was conducted by Petrus Rieke, who placed a heated mesh inside the tube instead of a flame. This made it clear that heat is the reason behind the emitted sound and not the flame itself. Through time, it was shown that this effect elevates when replacing the hydrogen flame or the wire screen by a stack of plates. The stack therefore plays the most important role in any thermoacoustic device, and that's why it is called the heart of the thermoacoustic devices. It is in the stack where the heat transfer occurs between the air particles and the stack plates. So, when one end of the stack is exposed to heating through a hot heat exchanger, the plates will heat up from this end, causing an increase in the temperature of the gas, while gradually lower temperatures happen to exist along the rest of the stack length. In other words, a temperature gradient forms along the stack. Once this temperature gradient surpasses the critical one, oscillations then take place as sound waves, which produce an output power. This could be interpreted as follows: considering a parcel containing a bunch of molecules at the point exposed to heating and installing a piston connected to a flywheel at the open end of the cylinder, heat is therefore transferred to the parcel from the heat source. This escalates the temperature of the gas molecules, which in turn gives rise to their kinetic energy, and so the molecules will definitely speed up and are able now to expand through the cylinder while losing their temperature to the adjacent plate. While traveling back, the same parcel is moving along the increasing temperature gradient. So the molecules of this parcel will therefore experience heating and the parcel will compress. With respect to a half-wavelength resonator, the gas oscillating would have the corresponding graph. With this said, the pressure is highest at the ends, while the highest velocity occurs in the center. To have the minimum viscous and thermal losses, a good practice is to position the stack at 1/8 of a wavelength from the closed end. And in order to get the best out of the stack, a distance between its plates must be around 2 thermal penetration depths. Because any parcel present beyond this range won't experience any heat transfer with the solid plate. On the other hand, a thermoacoustic refrigerator undergoes the exact reverse process. By removing the heat source and replacing the flywheel with a loudspeaker to produce sound waves, it happens now that we are in front of a new device. This device is what we call a thermoacoustic refrigerator. In this thermoacoustic device, which is the refrigerator, sound waves produced by the loudspeaker force the gas molecules in the resonator to oscillate, therefore reversing the thermodynamic cycle of its engine counterpart. The cold heat exchanger is now responsible for pumping heat from the space, which we need to cool down, into the device. And the role of the hot heat exchanger now is to remove this heat, which is now wasted heat, out of the system. However, half-wavelength resonators driven at high amplitudes at their resonance frequency were observed to experience nonlinear effects or periodic shock waves. To avoid this situation, which deteriorates the acoustic amplitude and affects the standing wave, a quarter wavelength resonator is used instead. And since a velocity antinode is present at its end, a buffer volume is attached to terminate it in order to simulate an open end and act as a region of zero velocity oscillations. In other words, it serves as an infinite acoustic impedance. So thank you very much for watching. Don't forget to like and subscribe, and see you in later videos.